Hello and welcome to another lecture in ECEN 215. Today we're going to talk about DC steady state circuit analysis. So this is part of the lecture series dealing with RC transients and RL transients. And what we're looking at here is how would you analyze a circuit that now has these new components, these inductors and these capacitors that cause these transients on the circuit. But what happens once we kind of analyze this from a steady state? So let's go ahead and jump in. So again, just to follow up and kind of as a refresher, what is a transient? A transient, again, is a temporary oscillation that occurs in a circuit because of the sudden change of a voltage or of a load. So this is represented again you've seen this from the RC transient lecture, where we have a voltage at 0 volts coming up to time is equal to 0. We apply some voltage to a circuit that has a transient effect. That would be a device that's like a capacitor or an inductor, and it causes this momentary oscillation to eventually, as time approaches infinity, will just decay and become a constant voltage. So we've applied, say here we have 1, 2, 3, 4, 5, 6 volts to the circuit. Because of the nature of these storage devices, they absorb and reply back energy to store and give energy, an inductor and a capacitor, in their ideal state. And so we have this decaying energy that occurs, and finally it steadies out to 6 volts. So that's what we're looking at here. And so we started with the lecture on RC circuits. We looked at a capacitor being switched on and off, and we saw how it decayed over time and would steady out. For instance, if you have a power supply, a series resistor, and then a capacitor, that whatever the power supply was, say 6 volts in this case, you would have this exponential decay where it finally reached, or increased, or where it finally reached 6 volts, and not this oscillatory nature. But it still had a transient where it wasn't 6 volts immediately at time is equal to 0. It took some period of time, as we learned, was related to the time constant of the circuit. So that's what a transient is. And now we're going to study what DC steady state circuit analysis means and what it's about. This is actually quite short section because this is fairly easy to do. So all we're doing here is we're going to look at a circuit with DC circuits that have these components, these inductors and capacitors, and we're just going to ask ourselves, what is the circuit doing when time is way, way greater than 0? Basically approaching infinity. What is happening? And that is what we mean when we say we're going to do steady state circuit analysis at the DC. Now we're going to be doing something called AC steady state circuit analysis later on in the semester when we get to AC signals. But for right now, we're looking at DC steady state circuit analysis, and we're considering what it looks like with a DC power supply, but with these devices. So let's start with, capacitors. For instance, capacitors, as time approaches infinity, way greater than 0, they appear to be an open circuit. So initially, we have a circuit that looks like this, where we have V of t across this capacitor. When there was a switch and this circuit was initially engaged at t is equal to 0, the current would actually is at that moment there's a extremely fast instantaneous change in voltage, and so I is equal to C dV dt, and so that moment there's a very high rate of change, but that rate of change is only for that brief moment since this was a DC power supply, and so the current is instantaneous at that moment. So as time approaches infinity and there's way greater than 0, what ends up happening is this capacitor gets as if it was not even there. And so it gets just removed from the circuit. Kind of like what we did with the Thevenin equivalence, where we removed power supplies, we removed current sources, and we replaced power supplies with shorts. Something similar is going to happen here. In this case, a capacitor, because of its nature, is just removed from the circuit. Likewise, an inductor, and we haven't, if you're following this in series, we haven't talked about RL transients yet, but effectively what ends up happening with inductors, they become what they are. They're just wires that have been coiled up, usually maybe around an iron bobbin of some kind, iron core, or just an open air core, but in the end, they're just wire. And so what ends up happening there, again, as time is approaching infinity, as time goes way, way past that in a transient state with a DC, an inductor just becomes what it is. It's just a simple wire. There's no longer a change in the magnetic field. The magnetic field is just what it is. It's steady state now, and it is now just a wire. So we take this inductor, just simply becomes a short circuit. So now looking and seeing how this is applied to a circuit. So let's take a look at that. So here we have an example. We have this now complicated looking circuit. We have this power supply. We have the switch that's going to close at t is equal to 0. We have this resistor here of 5 ohms. We have an inductor of 1 Henry. We're looking for the values of Ix and Vx. Let's say that's what we're being asked for here. We have this capacitor across R2. That's a 10 microfarad capacitor. If I was asking you to determine the transient nature of the circuit at t is equal to 0 to say t equals a few microseconds, this actually would be a little bit of a complicated circuit. In fact, actually outside the scope of this class, because this is actually a second order equation. We have two different differential equations going on here. But that's not what we're looking for. We're looking for the steady state circuit analysis, which means what? Let's apply what we just talked about. We're going to take and we're going to short the inductor, and we are going to replace the capacitor with an open. And the circuit becomes this. This is much easier to solve. It's just simply two 5 ohm resistors in series with a 10 ohm power supply. And this is just simply voltage divider. So we can solve immediately for Ix, which is just simply a 5 ohm and a 5 ohm resistor in series. So that's 10 ohms total. We have a 10 volt power supply. We can do the math in our head. 10 divided by 10 is 1. So Ix is 1 amp. Done. Solve that. Vx is simply the voltage across this 5 ohm resistor. Applying voltage divider principles, we have 5 ohms over 10 ohms, or 1/2 times 10 volts. Again, with something we can do in our head, just simply 5 volts. So we have 1 amp for Ix and 5 volts for Vx. So we took that complicated looking circuit and turned it into this by simply taking and replacing the inductor with a short and the capacitor with an open. So in this presentation, we discussed DC steady state circuit analysis, and particularly analyzing a circuit once the transient has passed. In particular, the important point to take away is that inductors become shorts and capacitors become opens. And then you just treat the circuit as you would with any standard DC circuit analysis at that point, and you can determine what the circuit looks like at a steady state. So again, if you have questions on this, please come to the Q&A session and we will expand in more detail. Thank you and have a wonderful day.